In this video, I'll go through the process of predicting the product of the hydrolysis of an amide. And so recall, amides represent the organic compound that has a nitrogen directly bonded to the carbon of a carbonyl. Hydrolysis reactions represent the reaction that involves an organic compound being broken down into two or more smaller organic compounds. During the hydrolysis reaction, water is added and the compound splits to give two separate compounds. And so if we go through the process, so the first step is to identify the bond in the amide that would be broken. This step is going to be the same regardless of the amide. Because of the different types of bonds that are present, you have covalent bonds that are polar and nonpolar. Nonpolar indicates the electrons are evenly spread out, so those atoms where the nonpolar bonds are located are happy. They are stable. Things are being shared evenly between the two. However, polar bonds indicate an uneven distribution of those electrons. Instead, you'll have one atom in that bond that is trying to take all of the electrons in the bond. So carbon-oxygen bonds, as well as carbon-nitrogen and even nitrogen-hydrogen, those are all covalent bonds. So I'll just redraw this structure and point out all of the polar covalent bonds. So I'll make it a little larger so that it's easier to see. I'll also show, when you see that NH written like that, that simply indicates that there's a bond between that nitrogen and that hydrogen. So here we have the same molecule. And so we have those carbon-nitrogen and we have a carbon-oxygen bond. All of these are polar covalent bonds. So I can show the bond dipole. Bond dipoles simply indicate how the electrons are being attracted within those bonds. And so the more electronegative atom is able to attract or pull on those electrons. And so we have this carbon that is bonded to two electronegative atoms, or two more electronegative atoms. So they're pulling on those electrons. So you have this carbon that is kind of having a tug of war type of thing going on, where the oxygen is pulling on the electrons, but the nitrogen is also pulling on the electrons. So that carbon is trying to be pulled in two different directions by two different atoms. That creates an unstable carbon. It's not happy being pulled in two different directions, and so if it could get rid of something, that's what would happen. If we look at the other polar bonds, you simply have a carbon-nitrogen and a nitrogen-hydrogen. They are both being attracted towards that nitrogen. So you don't have that tug of war in two different directions as you do with that carbon. So because of that tug of war with the carbon being pulled, that bond is always going to be the more reactive bond. Because if that carbon could get rid of that bond, then even though it'll still be pulled, it won't be pulled in two different directions. And so as you go to draw the product, simply redraw this compound without that bond. So I'm going to redraw that N where my carbonyl was located. I'm going to redraw the opposite end. So I'm going to show them as two separate compounds because that bond is broken. So these two atoms are no longer connected to one another. They're no longer attached. What happens from there, because water was a reactant, so we saw water on our reaction arrow. Whenever things are shown to the left of the reaction arrow, above or below the reaction arrow, that indicates that you're dealing with a reactant. So if we think about the water compound, water, H2O, so the Lewis structure of water is this. We have an oxygen that is bonded to hydrogen on both sides. And so oxygen-hydrogen bonds are polar. These are very polar bonds. Those electrons are being pulled towards that oxygen. So even though that oxygen is able to attract the electrons, it doesn't take the electrons. So it doesn't have an actual charge, but it feels as if it has a charge because it's pulling on those electrons, which are negatively charged particles. The hydrogen atoms then feel as if they are missing electrons because that oxygen is able to pull very hard on those electrons. Oxygen is the second most electronegative atom. So when it pulls on those electrons, the hydrogen then feels as if it is missing electrons, causing it to have a partial negative charge. So keeping this in mind, we can think about what would happen when the when the water molecule is added to that amide. One thing that I would recommend when dealing with hydrolysis reactions, regardless of what reactant is undergoing hydrolysis, think about your water molecule as H and OH. Because this is how it ends up getting added to those two new compounds. One gains in H, the other gains in OH. Thinking about those partial charges that we just discussed. That H was already determined to have the partial positive. That oxygen was determined to have the partial negative. So keeping that in mind and also thinking about the polarity of your original reactant, that will help you with determining which end gains the H and which end gains the OH. So going back to our original compound, we had our amide. We've already determined that there were polar bonds present. So looking at where the bond broke, the carbon, it was not as electronegative. The electrons are being pulled away from that carbon. So the carbon would feel as if it has a partial positive. The nitrogen was more electronegative. It was able to attract those electrons. So that nitrogen would feel as if it has the partial negative. And so remember, in chemistry, opposite charges attract, like charges repel. So if I have a partial positive on the carbon of the carbonyl, it's not going to want to be paired next to another partial positive. Instead, it would want to be paired with a negative, the opposite charge. Opposite charge. And so this becomes the OH. That nitrogen, which had the partial negative, it wouldn't want to be paired with another negative. Instead, it would want to be paired with the positive, which is where the hydrogen comes in. And so you end up with these two new compounds where you have the OH that was added to one, the hydroxyl that was added to the other. The OH that was added to one, which is your hydroxyl, and the hydrogen that was added to the other. So you end up with the carboxylic acid and the amine. If we were doing the hydrolysis of an ester or the hydrolysis of a thioester, we would stop at this step. We've created our carboxylic acid and our heteroatom containing molecule. However, when you are looking at the hydrolysis of an amide, at this point, we have a carboxylic acid, which is a weak acid. We have an amine, which is a weak base. Whenever you have an acid and a base in the presence of one another, an acid-base reaction can take place. Recall that acid-base reactions involve a proton that is transferred from one thing to the other. The acid loses a proton. Remember, protons are simply hydrogen ions. The base gains a proton. So because that acid and base are together, an acid-base reaction occurs. And so this is the extra step that must be taken when dealing with the hydrolysis of an amide. The acid will lose a proton. The proton or hydrogen ion that is removed is the hydrogen that is the most unhappy. Think of it that way. You have lots of hydrogen atoms in this compound because remember, at each carbon we have multiple hydrogen. But all of those create nonpolar bonds. The electrons are evenly spread out. Those carbon and hydrogen atoms are happy. Those hydrogen atoms bonded to the carbon are fine being bonded to the carbon because the carbon shares the electrons. But then you have this hydrogen bonded to oxygen. Oxygen is the second most electronegative atom. When it's bonded to hydrogen, it tries to take the electrons away from that hydrogen, creating a hydrogen that is not very happy. So what ends up happening is that this weak acid will lose that proton. When you're losing the proton, protons are hydrogen ions. More specifically, they're hydrogen cations. So thinking about this carboxylic acid that forms. So I'm going to draw the carboxylic acid initially, just so that I can show what I'm talking about. So when you see that OH, that is the same thing as saying I have an oxygen with a bond to a hydrogen. When oxygen has 2 bonds, it also has 2 pairs, so a total of 4 non-bonding electrons. When the acid loses the proton, it loses that hydrogen. Remember, anytime you see bonds between 2 atoms, that indicates that those atoms are sharing 2 electrons. However, in the case of a proton, that hydrogen cation means that the hydrogen doesn't have any electrons. So essentially what we have is a hydrogen that leaves behind that electron. So now, instead of that oxygen owning 1 electron in that bond and that hydrogen owning 1 electron in that bond, now that oxygen owns 2 electrons in that bond. So it gained an extra electron by that hydrogen ion being removed. So when it gains that extra electron, so we can't leave it as a bond because bonds indicate 2 atoms, but now that oxygen has those 2 non-bonding electrons. So it now has an extra electron, meaning that it has an actual negative charge. But what happened to the proton? So now let's think about the other part. Let's think about the base, because the base gains a proton. So if we look at that amine, so that nitrogen has 3 bonds, so we can see 2, 4, 6 electrons. Whenever nitrogen has 3 bonds around, it has 2 non-bonding electrons. Again, non-bonding electrons belong to that atom. However, remember, we still have this hydrogen. I'm just going to show it down here somewhere. We still have this hydrogen that is floating around, that doesn't have any electrons. It's just floating around in space. So we now have this nitrogen that has extra electrons that it could share with the hydrogen. When those extra electrons are shared with that hydrogen, I'm just going to show this bond. I'm going to rearrange some of these bonds just for space. So when that new bond forms between that nitrogen and that hydrogen, the nitrogen was able to share its electrons with those electrons with that hydrogen. So it lost an electron because now in that bond, nitrogen owns 1, hydrogen owns 1. Whereas originally, the nitrogen owned both of those unpaired electrons. Now it only owns 1, so it lost an electron. Whenever atoms lose electrons, they end up forming positive charges. And so the additional step that you must take when dealing with the hydrolysis of an amide. So you'll still go through that same process. You'll have some amide plus water in the presence of a catalyst. You'll then end up breaking the bond, the single bond between the carbon and the heteroatom to split the compound. One end, so the end where your heteroatom is located, will gain the hydrogen of the water molecule. The hydroxyl of the water molecule then adds to the carbonyl containing part. This gives you your carboxylic acid and your amine. You would normally be finished. However, carboxylic acids are weak acids, amines are weak bases. Anytime an acid and a base are in the presence of one another, an acid-base reaction will take place. So that proton will be removed or lost from that carboxylic acid, but the base, which is your amine, will then gain the proton. So when dealing with the hydrolysis of amides, you won't actually stop at the carboxylic acid and the amine. Instead, you would have the carboxylate, which is the conjugate base of your weak acid, and you'll have the protonated amine, which is the conjugate acid of your weak base. Conjugate acids and conjugate bases are topics that were discussed in 1151. These simply indicate a difference of a proton. The conjugate base is formed after the acid has lost a proton. The conjugate acid is formed after the base has gained a proton. And so, whenever dealing with the hydrolysis of amides, you must make sure that you don't stop at the carboxylic acid and the amine, but instead you go on to allow that acid-base reaction to occur, because it will, and show the products as the conjugate base of your carboxylic acid and the conjugate acid of your original amine. So we can go through and do another example just to make sure you're good on it. I won't go through step by step as we did just then in showing all of that, but we'll still go through and solve another hydrolysis reaction. So let's say tell you what, I'll turn this into a ring just to show that it can be basically anything. I can even have this is my amide, and I can go on to do my product. Again, regardless of what your amide is, go ahead and start by redrawing that same compound. It's still going to be that carbon heteroatom bond that breaks. So that bond here is the bond that's going to break. So we'll be able to separate our original reactant into two compounds. From there, we can add water. The hydrogen is added to the heteroatom portion. The hydroxyl is added to the carbonyl portion. But again, we now have a weak acid and a weak base. So we won't stop there. Instead, this proton, so that hydrogen ion, will be transferred from that acid to that base. So the actual products of this reaction would be the conjugate base. So the result of that acid losing a proton, the conjugate base is going to have an overall negative charge because that oxygen was able to keep the electrons even though the hydrogen is no longer present. Then our second product will be a protonated amine. Protonated amine simply means that it has an extra proton. So it has an extra hydrogen, causing that nitrogen to then have a positive charge. So this would actually be the product of the above hydrolysis. And so again, anytime dealing with the hydrolysis of an amide, the process is still the same as with the ester or the thioester. You'll break that carbon heteroatom single bond to split it into two compounds. The carbonyl portion will become your carboxylic acid by gaining the OH. The heteroatom portion, in this case, becomes the amine by gaining the hydrogen. If it were an ester, it will become the alcohol. If it were a thioester, it will become the thiol. But the difference between the amide undergoing hydrolysis and the ester or the thioester is that now that we have this carboxylic acid and amine, we now have an acid and a base together. So the reaction will continue because now an acid-base reaction takes place to form your conjugate base and your conjugate acid. Again, a conjugate acid and a conjugate base simply differ from the original acid or base. They only differ by one proton, so one hydrogen ion.